Quick, group 3.
Johnny, hurry up.
Have you seen me on what?
Yeah.
I think it doesn't have our front on it. We'll just switch this.
Take his desk. 135. Holy shit. That's crazy.
Give it back to me after you guys sign.
Oh, no, it's still up there.
Oh, is it up?
Yeah.
Sorry. Why did we take it back? Oh, you stapled it. Yeah.
Wow. Thanks.
You guys can just stand here.
Wow. He's 25. All right. What's the? Yeah.
Okay.
What's with this?
All right.
You want to turn the lights off? Wow.
Wow.
Ah.
Thank you for coming today, everyone.
Are you
This is our
impressed now?
digital pixel project.
Yeah.
So, as you all know, we were tasked with designing a CMOS camera on a chip, and just a little bit of our executive summary. We successfully used a 12-bit binary counter. We were able to implement the HDR feature, overflow protection working as well, and 1.2 volt recharge successful. And we have full schematics simulations, and in total we used 488 transistors. So this is our full pixel schematic, and I won't go too deep into it, but just as a general overview, how it works. Starts with the global reset, pulling the PMOS on, so the VN turns on to 1.2 volts, and then this starts the integration phase, where light coming from the light incident on the photodiode means that the VN discharges at a rate that is proportional to the intensity of the light. And then once VN drops past a threshold, which is 0.6 volts for our case, the comparator flips and it goes through the delay chain, and the output of the delay chain will then go to the 12-bit HDR counter. And the HDR counter has we have a feedback overflow protection circuit to make sure that once it's full, it doesn't take over from 11111 to 00000. And the role of the delay chain in this is to make sure that the ASR line is held high for long enough so that the VN node can charge fully back up to 1.2 volts. But yeah, we'll go into each component, and first is the comparator.
The comparator. So we didn't try to do too much with regards to min-maxing the size of this outside of just firstly achieving what was explicit in the document preamble. So that was pretty simple, just because you could easily instantiate the simulation and then just change the ratio between the NMOS and PMOS. And we found basically 1 to 2.67 to be a really good ratio to achieve about just about 0.6 volts. I then tried to sort of scale back the NMOS size and keep the ratio, but then what I found was that the ratio actually widened, so you'd have to have a significantly wider PMOS to achieve the 0.6 millivolt desired output. So yeah, we just stuck with the 1 to 2.67 and 1 micrometer comparator. So I guess moving on to the
Delay chain next. So I was responsible for the delay chain. For our delay chain, we found that we used 18 inverters, and we determined this iteratively, because at the start we were trying to calculate it, but it was quite difficult. So we decided to just take Cash's advice and just put a whole bunch of delays and make sure that it works and fully charge to 1.2. And then afterwards, we would slowly reduce it in 2s to make sure that the polarity is still the same. And yeah, so this is just the some of our what do we call it, simulations. So this is the VN node and showing how the number of inverters changes, how long it stays, the ASR stays off. So how long VN charges, and you can see that at 20 inverters, it goes up to 1.22. 18 is 1.21-ish, and then 16, it doesn't hit the 1.2 threshold. So at this point, we decided, okay, 18 inverters is the amount that we need. And then as for the inverters of the delay chain, so as most of you probably know, the delay chain is made of just a series of inverters. For the sizing of the inverters, initially we went with the smallest possible because we were concerned about size. And we also know that the smaller the width is, generally speaking, it's a slower transistor as well, so it's kind of a win-win in that regard. But again, as Cash mentioned in his lecture very generously, the smaller transistor actually, the smallest possible transistor, I think it was 160, actually made a bigger area because of how the DRC rules work. So we went with 280, which is matching the source and drain width, which allowed us to make it a lot more compact. But so that's the overall layout. We ended up having to kind of fold it back on itself as it fit our overall design better. But so next was the 12-bit HDR counter by Seb.
Yeah,
Oh.
so,
John.
sorry.
John.
Yeah, so this is our symbol for our 12-bit HDR counter. As the name suggests, it is capable of doing the high dynamic range function. We achieved this with some specialized hardware, integrating a multiplexer and a frequency divider, which we will cover later. It has your active low reset, clock input, and your 11-bit stream output, and a grounded VCC. As you can see, this is the physical layout of the device. I mean, here you can see all the different flip-flops we use. This 13th one here is the flip-flop we use for our frequency divider, and then we have the multiplexer up there, and then here's the full schematic for it. You can see the frequency divider is right here, the multiplexer here, and we were able to avoid using an extra inverter on the multiplexer here because we just use the inverting output from the final 12th bit as the inverter control signal for the multiplexer. This is our proof of concept for the HDR functionality. This diagram here is quite representative of our design process because it obviously is very expensive to run a full 12-bit design of simulation. It takes about 50 minutes to simulate the full thing. But if you do an 8-bit simulation, it takes about, 20 seconds to do that? So it's much quicker. I mean, furthermore, it's also just a lot easier for the audience to read this diagram than the 12-bit one. You can see right over here is when the HDR triggers because the most significant number goes high and the clock frequency slows down.
So yeah, just going back to the D flip-flop of it, obviously I won't bore you with the initial schematic as I'm sure everyone's quite aware of that. We did initially try to go with a JK flip-flop design, however, pro tip, don't do that. But yeah, basically, once we got to the layout, because we were just trying to keep it as simple as possible, we just sort of instantiated the gates and then just went from there. And we're able to get, even though it's obviously not the most efficient sort of, I guess, layering with regards to sharing gates sort of vertically, it's still got, I guess, acceptable area, and we're able to fit it quite nicely into the overall cell. Obviously, as Owen mentioned, we were initially going for 160 as well, but then we just bumped it up to 280 because we didn't really lose any sort of space. And it was just, yeah, I guess, better performance.
Yeah, so as for the HDR implementation, we all kind of had a go at trying to design some kind of way of doing it, but we ended up going with this design, which is basically, so on the right side here you have like the rest of the flip-flop, the rest of the binary counter. So this is the first or the 0th bit of the binary counter, and instead of directly feeding the delay chain clock signal into the first bit, we instead have this little HDR implementation circuit on the right over here, and it involves having a frequency divisor and a multiplexer. So it's fairly simple. The multiplexer chooses whether the first bit comes from directly the clock signal here, or it comes from the frequency divider. And as the name suggests, the frequency divider, it makes it so that it needs 2 clock signals for it to pass through one. And so the select line for the multiplexer will come from the largest, the most significant bit, so the 12th bit, which will then, it'll switch the output when the 12th bit goes on. So instead of taking the clock signal directly, it takes half the clock signal. And so that's how we implemented the HDR.
This is our 2-to-1 multiplexer we use for the HDR. As you can see, we use pass transistor technology to pass the either A or B outputs depending on the select channels. I think it's quite standard that we use PMOS and the NMOS in parallel with one another, because the PMOS passes a strong 1 and the NMOS passes a strong 0. Yeah.
Yeah, and as he said earlier, we were able to save on 2 transistors actually, because a normal, like if you look up a MUX, a 2-to-1 MUX online, usually they have like another inverter here, but because obviously our select line is coming from the 12th bit, and the 12th D flip-flop already has a NOT Q, so we didn't need to have the extra inverter there. We can just run it through, and that was just a little extra space saving we could have. Next is the feedback circuit.
Okay. So for the feedback circuit, we went with multiple different iterations of it. Our first initial concept, which we brought to Cache, was our 4-stage NAND gate, which had essentially 11 NAND gates all inputting into one another. Cache basically said it was a stupid idea and said to watch next week's lecture and he'll explain why that is. It was apparent when we watched the lecture that it's because of the logical effort of all of the gates. Made it such that the propagation delay was larger than having that of the 12 input NAND gate. Additionally, one other solution that we were looking into was having a supposed 13th bit of a flip-flop. Once that 13th bit is high, it becomes 1. The rest of all of your flip-flops are 0. Then the 13th bit flip-flop essentially sends a pulse down to all flip-flops, setting them all high, and then shutting down the 13th bit. Unfortunately, we didn't go with this design because we found that the number of transistors required was too great. Not only because you had to include a 13th bit flip-flop, but you also had to add the functionality in the other 12 flip-flops. So that was another reason why we didn't go with that. So ultimately, this is the approach that we went with, where all of the inputs of your binary counter, all of the outputs, are fed into your big mega NAND, which is our 12 input NAND gate.
If you don't mind me adding in, our HDR scheme using the frequency divider divider actually enables the mega NAND gate to work as a overflow protection. Because if there was no frequency divider, then the NAND gate would be too slow. The clock would tick once more, which would erase a binary counter. However, because of the frequency divider, it means that the binary counter only clocks every second, every second like tick, every second clock cycle, which means that the NAND gate is guaranteed to be faster than the next clock cycle every time.
So again, as Johnny mentioned earlier, we went with I guess an 8-bit simulation just for ease of simulating. We can see here that once the most significant bit has been reached, that all of the signal from the photodiode immediately drops down to 0, and the clock essentially gets locked. So the binary counter gets locked.
Yeah, just a bit of a closer look into the graph. Yeah, you can see how the VN keeps going up and up and up, up and down, and then once all of them hit 1, it goes one last time. And if actually at this point here, if there was no frequency divider, it would actually trigger one last comparator flip because it goes from above 0.6 to 100.6. But as you can see, all the all the outputs stay at 1 because of the frequency divider.
Beautiful.
It's a bit simple. It's actually my favorite symbol.
Okay.
Yeah, so this is our schematic and layout. I think an interesting thing you might notice about the layout is the gate's quite bent. This was, when I was designing it, it was quite difficult to have the gates lined up properly, so I had to bridge the PO layer across. Yeah, next slide, please.
It's the reset
So
circuit.
now the reset circuit is a standard requirement presented to us. It required that we have both a global reset pin as well as an asynchronous reset. So the global pin reset, as Owen mentioned at the very beginning of our presentation, serves for the purpose of beginning essentially the whole system of the camera on a chip. So once that's been set high, the system essentially starts. The ASR serves a dual purpose, one for overflow protection and 2 for bringing back the clock signal once it reaches a certain threshold, bringing it back up high, which then drives your ASR pin, bringing your VN high slowly, and then going through a comparator and sort of looping through over and over again.
Yeah, photodiode, pretty self-explanatory. Obviously, came with the preamble, but we were trying to sort of saturate our HDR counter, and we found that sort of just within the, I guess, 100 microsecond time frame, 2.8 microamps seems to sort of get it to saturation just, but we'll be sort of testing that more decisively tonight.
For our initial work, we found a few areas where it needs improvement. The general consensus is that we can improve by creating a faster design, using dynamic logic. We can also optimize power consumption, and we can condense the layout so it takes up less space than 30 micron by 30 micron.
I think we're also going to try, particularly, I guess tonight as well, is just make sure that the instantiation of everything in the layout sort of like works, I guess, because I think with the mosaic stuff, I think we still need to just make sure that with all of our sizing that we have, that everything is sort of kosher.
Yes.
So I
Which group are you in?
Group 1, sorry. So we got a question about that. Do you have to do your layout, post layout for your mega feedback circuit, and is that is a delay acceptable?
So
What's the layer simulation?
Post layout simulation for the Meganand.
The delay simulation of the Meganan you wanted to see. We don't have it in the presentation, but we can provide it upon request at a later date. Yes. Tomorrow, if you're interested, we can provide it.
So post layer simulations show that delay is acceptable.
so yeah.
Yeah.
Because
Is
of
it
the
acceptable?
you mean for the feedback circuit and whether it
Yeah, because
successfully.
let's say your Mega N and circuit, you use many pure one metals to connect to each others.
Yes.
In your case, the big capital
Yes.
between. So
Yes.
I wonder if that delay is acceptable in your post
Yeah,
layer.
there's a lot of room for error for the delay because, as we covered, the clock, once we get to the 12th bit, the clock, halves in frequency. Right, so
You go,
every
PC
it takes
is
2
here.
ticks for
yeah.
the takes 2 clock ticks for the signal to actually propagate. If that makes sense. And so
Yeah, it's
so
almost like a
that
buffer, the
I-
frequency divider.
Yeah.
and so there's no, it eliminates the race conditioning essentially.
Yeah.
And could you please show your pixel?
Sorry.
Pixel?
Oh, yes. Maybe the first slide.
Oh, beautiful.
Yeah, pixel. Where is your outline?
So you mean the upper line?
Upper line,
Yeah.
right here.
It's 12.
Yeah, there's 12
Yes, that's the
just pass transistors.
Can you please show your Moscow? Mosaic.
Mosaic.
Mosaic, yeah.
Could you connect to each other? The upper line?
Sorry, the lines, are they connected? Like,
Is
Yeah.
it? Okay. Yeah, that's all. And one last question from the.
I got a limit group 1 to ask final question.
Okay.
it's good, he's curious, he wants some
Well,
product.
if it's a feedback question, it's okay. Like if you are responding to their answers, that's good. But if it comes to a new question, you guys take some chances for other groups. Nah, cut it off. Yes.
Is there any special consideration? Group 2. Is there any special consideration when it comes to the length of transistors used in installation? That so you use other.
Yeah, so I didn't actually include it in here, but I did do some testing with the length, and opposite to the width, the longer it is, the longer the transistor is, the longer the delay is. But we found that kind of the ratio that the delay increased. Sorry. Yeah, for the delay chain. Are you talking about the inverter length, or how many inverters?
Channel length or number
Channel
of
or number?
channel length?
Channel length. Yeah. So for the inverter, so like as I said before, like we know the lower the width, the faster it is. Oh, sorry. The lower the width, the slower it is. But for length, it's opposite. So the longer the width, the higher the length, the longer the channel length, the higher the delay, right? So we did test making a longer channel length, and like try to see what the propagation delay was. But I don't exactly remember from the top of my head, but I tried like doubling the channel length, but it only increased the delay by like 40-50%. So I guess we kind of decided, it's not worth increasing the length, and we'd rather just add more transistors.
But you're not using minimum length.
Good.
You use 130.
Yeah, that's
think that's an old.
Minimum is 120.
We definitely yeah.
Oh.
And
That's a typo.
that's a
Typo on the schematic as well?
nah.
Is
It's
that-
got yeah. No, it's on the
Okay,
what's
well, I think we're just
Oh.
idiots.
Um, Yeah.
Last question.
Regarding the delay chain,
Yeah.
if you have the consistent width, why wouldn't you like share the diffusions to like around
Sorry, say it again.
Show the diffusion.
grains were like the weedy and round were overlapping, and that would cause them to
I think it was because
Which this and this?
I think it was because
Share diffusion, right?
Oh.
Are you guys group 5?
Yeah, that's a.
wasn't it because I thought it was just because we had like an excess of horizontal space at the time, and we were just focusing on minimizing the vertical, and that's why the ground and everything is just on a second level because we didn't really. I guess it wasn't really a concern at the time, but yeah.
Yeah, we don't really have a lack of spare space. We find we had an adequate space, so we didn't have to apply excess effort into optimizing space. But that is a future
Improvement.
It is a very much future interest as we highlighted in the final slide.
Responding to that?
Somewhat in response to that. With the delay chain, you're using the same size inverter
Yeah.
for each stage in the delay chain.
Yeah.
Is there a reason why you chose to do that instead of progressively sizing them to try to minimize the amount of delay? Because ultimately, if you minimize the delay, you can make it faster.
Well, I guess for the sake of the pixel, the delay chain, you actually want it to be, as short as possible, but you still want it to be past a certain threshold. Like if you look at one of these, it needs to be, the delay has to be a certain amount of time so that it can charge to 1.2 volts. So there's not really a point for us to, well, we thought there's not really any point to optimize how fast the delay is because the whole point of delay chain is to add a delay. So, yeah, that's.
Yep, thanks. Just a final comment. I appreciate the thing that you have considered about your feedback, the MegaNet. Yeah, since you guys have done the HDR, it's a very good advantage in terms of the feedback. So we can have a simple 12 input NAND gate, and then you can get the job done, which is good. And also appreciate this, that you've shown some considerations, and also two more things. One is that this is, in terms of presentation skills and stuff, you guys are presenting this in the perspective of as an audience. So when audience see this, it is quite clear. One good thing about that is that you don't just show all the 12 bits, you only show 8 bits or 6 bits. It is a lot clearer. In principle, it's the same. So you have already demonstrated what you want to show, while you don't overwhelm the audience, which is very good. But too many cache mentioned in your presentation.
Okay, sorry.
So it depends on,
Yeah.
say, if I'm your customer, it depends on whether your customer likes to take credit or not.
Yeah.
I don't, so
Right,
it's a
okay.
major drawback for me. But so you need to know your customers before you present, and also you are using inconsistent notations. So in some of them you use VCC, some of them you use VDD.
Yeah.
And VCC is only using BJTs.
Yeah.
And in fact, we use VDD. That's why when you do designs, don't use your own convention, use the standard ones. Yep,
Okay.
Yeah.
after all, it's good.